Alright, here we have FRQ practice math. I'm going to go over problems 1 and 2 right now. So before continuing, go ahead and read over the question carefully, and then we'll get started with letter A. Letter A asks for the number of kilowatt hours of electricity by the plant in a year. So for letter A, I'm going to take the plant, which can produce 18 megawatts of power, and I get that number up here. The capacity of the power plant is 18 megawatts, and it says that it runs at full capacity for 8,000 hours per year. So it's asking for the kilowatt hours. So I'm going to take 18 megawatts times 8,000 hours per year, and that gives me 144,000 megawatt hours per year. But it's asking for this answer in kilowatt hours. So 1 megawatt is equal to 1,000 kilowatts. So I basically need to multiply this by 1,000, which is adding 3 more zeros. And this is our answer. Kilowatt hours per year. On an FRQ, you make sure you have units in your problems and units in your answer, and as best you can, set it up linearly, like this. Letter B. At the current rate of electrical energy use per household, how many kilowatts of electrical energy does the community consume in a year? So up here we find out that there are 5,000 homes, and it tells us this here, 5,000 homes in the community, and each household consumes 7,000 kilowatt hours. So this is a pretty easy math problem, as long as you can find out the numbers that it wants. So 7,000 kilowatt hours per year per home times 5,000 homes in the community. And so 7,000 times 5,000 gives us 35 million. So I'm just going to take 7 times 5 equals 35 and then add my zeros, and so there's 6 zeros altogether. And this is in the community. Kilowatt hours per year in the community. This is a pretty difficult number to use, so I'm going to change this to scientific notation. You could leave it like this, and it is a correct answer, but it's better to actually change it to scientific notation. So you go 1, 2, 3, 4, 5, 6, 7. 3.5 times 10 to the 7th kilowatt hours per year. The reason I want it like this is because the next problem will be easier if I have it in scientific notation. So letter C. The first thing we're going to do for C is we're going to take the cost of the turbines. So we have 10 turbines. It tells us in our givens up here, 10 turbines. And the cost of the turbines is $4 million, and they're going to run for 30 years. And so 10 turbines, and they're $4 million each to purchase, so 10 turbines times $4 million. And I'm going to actually, instead of writing the word million for this, I'm going to put it in scientific notation. You should memorize that 10 to the 6th is a million, and that is per turbine. So my turbines cross out, and it's going to cost 40 million to purchase all of the turbines. And this is not correct scientific notation, so I need to move the decimal point over once, and so that's actually going to be 4 times 10 to the 7th. And that's a better answer, but actually I'm not going to circle it because this is not, we're not finished here yet. So what we need in the community from this problem here is 3.5 times 10 to the 7th kilowatt per year. That's what we need in this community. So over 30 years, 3.5 times 10 to the 7th kilowatt hours per year. And we are going to run these turbines for 30 years, or yes, for 30 years. And so 30 years is up here, and the years cancel out. And so 3.5 times 30 is going to give us 105 times 10 to the 7th kilowatt hours are needed for those 30 years. Now what we're going to do is we're going to take the cost of the turbines and divide it by the kilowatt hours to see how much this power actually costs us for the wind energy. So we're going to take $4 million. Actually, this is $40 million, excuse me. And we're going to divide that by 105 times 10 to the 7th. Now, I left this number in improper scientific notation because really this should be 1.05 times 10 to the 9th. But I left here at a 7 because this one's at a 7 and it makes this math really easy. Because basically the 10 to the 7ths just cancel out. So now we've got 4 divided by 105. And so we have to do this by hand on an AP test. So if I do it by hand, I have to do this big, long division problem. Etc. So when I finish out this long division problem and I do it by hand, I'm going to get, and it's going to round to 38 cents. So the cost of the dollars per kilowatt hour here, I'm sorry, this is per kilowatt hour. So I'm going to get 38 cents, 0.038 cents, excuse me, per kilowatt hour. And that's how you do the last part here. The last part C is a pretty complicated question. So on an FRQ, if you can do parts A and B, which are a lot easier, but you mess up on C, that's okay, because C would probably just be a point or 2 points of the entire 11-point question. And you only need about half of the points on each FRQ to pass the AP test. So even if C is confusing and you didn't get it right because there's a lot of parts to C, it's okay. You can still get a very good score on the AP test even if you mess up on C. But work really hard to get some of the easier math problems done. Even if C is confusing, A and B are more straightforward. Okay, turning over to number 2. Number 2 has here 4 givens for 1 answer. So the first thing that we're going to do here is we're going to find out how many gallons of gas are needed per car per year. So a car drives 12,000 miles per year on average, and 1 gallon of gas lets you go 25 miles because it's 25 miles per gallon. So miles per gallon really is like 25 miles per gallon, like that, miles. But you could flip these over too, and it's correct because it's just a ratio here. So my miles cancel out, and I end up, when I do this by hand, 12,000 divided by 25, I end up with 480 gallons of gas per year. The next thing I have to do is take my answer here, 480 gallons of gas, and I need to multiply that, that's per year, by 160 million cars. I'm going to leave it like this for now, but I could change that to scientific notation. If I did change it to scientific notation, actually, you know what? I think I will change this to scientific notation. It'll make my problem easier. So 160 times 10 to the 6 is the answer, but this isn't good scientific notation. It's actually 1.6 times 10 to the 8 is a better answer. And so now I can multiply 480 gallons times 1.6, and I'm going to get the total number of gallons needed of gas per year for all the cars. So doing it by hand, you're going to end up with 768 times 10 to the 8th gallons of gas. The cars cancel out because this is gallons per year per car, and so this car is actually up here, and this is going to, I'm sorry, yeah, it's like this, and the cars cancel out. So we end up with 768 times 10 to the 8th gallons. This number here, again, to change it to proper scientific notation, we're going to move the decimal point back twice. So it's 7.68 times 10 to the 10th gallons of gas. So if 20% of the cars could be replaced with electric vehicles instead of burning gas, then we're going to take this answer and multiply it by 0.2, because 20% is equal to 0.2. So I can take this answer and I can multiply it by 0.2 here. And if I do that, I end up with 1.536, and I'm just going to use this number here, times 10 to the 10th. And that's how many gallons of gas that are saved.